Right. Today we're going to talk about putting signals in and out of PLCs. There's two types of signals we put in and out. The digital signals, they're the on-offs. So things that are on-off, start-stop, normal alarm, on, well, that sort of thing. We call them digitals, and you have digital in and digital out. Then we have the continuous signals, the 4 to 20 milliamps, 1 to 5 volts, that sort of thing. And we call those analogs in and analogs out. So that we have these four basic types of signal. Signals in and out of PLCs are called points. And we're always talking about points and point counts. That's how you compare different PLCs. You say, oh yeah, this PLC has got 10,000 points, or this PLC's got 5,000 points, on the control system, I should say. And we compare PLCs the number of points, which are the number of ins and outs that the thing has. You have digital ins, which we call DIs, and digital outs, which we call DOs. You have analog ins, which we call AIs, and analog outs, which we call AOs. There are some slight variations on the theme. Some digital ins, and digital ins being signals where all we're doing is we're detecting whether it's on or off. Some digital ins, we don't actually detect the on-off state. What we do instead is we count how many times the thing comes on. Because there are some instruments which give out little pulses. And what we do is we count the pulses. And we call those, sometimes we call them PIs, pulsed inputs. It's basically a digital input, but instead of just seeing if it's on or off, we count the pulses. The sort of instruments which give out pulses are basically encoders on some sort of rotating machine. If you have some sort of rotating wheel and you have an encoder on that wheel, then you get pulses, and the faster the pulses come out, the faster the machine is moving. Another machine which gives out pulses is any type of meter. So pulsed inputs come from things like water meters and electricity meters. So water meters and electricity meters give you pulsed inputs. One thing to make sure of is that the PLC can run fast enough to see all the pulses. You see, PLCs have a thing which is called the gate time. And the gate time is the time which the PLC can see a pulse in. So if a PLC has a gate time of 200 milliseconds, if PLC has a gate time of 200 milliseconds, that means it can see 5 pulses per second. You have to make sure that your PLC has got a gate time which is fast enough to be able to see whatever meter you might have. Because if your PLC can only see 5 pulses a second and your meter's giving out 8 pulses a second, you'll only see 5 of those, which means that you'll undercount the pulses. Now, because an electricity meter and a water meter and a gas meter, these are things that we normally bill with, that means that we will underbill the client. That can be a big problem, because later on Western Power or Alinta Gas will come along and say, hey, look, you used all of this gas, but you've only paid for this amount. And, well, that tends to lead to a few little upsets. When we're going from the PLC world out to the real world, this section here, this is the PLC world, this is the real world, When we're coming from the real world into the PLCs and going out of the PLCs into the real world, firstly, the physical world, we sense the physical world with sensors. We condition those signals, in other words, we change it into 4 to 20 milliamps. So here's 4 to 20 milliamps, for instance. And then we need to take that 4 to 20 milliamps into the PLC world. We do that. It's an analog signal here. Never a good thing to abbreviate. It's an analog signal to out here. And what we do is we take that analog and we convert it into digital. To do that, we use an analog to digital converter, which is abbreviated ADC. So we take the analog signal, we convert it to the digital signal using an analog to digital converter, an ADC. Then we make decisions. We got PID blocks, we got all sorts of fun blocks. We make decisions, or we display those values, and then we have to output back to the real world from the PLC. To get the digital PLC values, oh, and by the way, I should mention that inside a PLC, signals are always called counts. It's a historical thing. Now, we're going to go from counts, which live in the digital world, back out into the analog world. To go from digital to analog, we use a digital to analog converter. And that allows us to go back into 4 to 20 milliamps, out to an actuator, some type of valve, and that affects the physical world. So we come in using an ADC, and we go out using a DAC. Okay. An ADC is a complicated piece of machinery, so the first thing I'm going to do is I'm going to explain how a DAC works, because a DAC is quite simple. Now, the first thing you need to know is that I am not an electronics person. I loathe electronics with a passion. I never understood it at college, and I still don't understand it now. So, this is my understanding of how these things work. You have, in electronics, a thing called an op-amp, operational amplifier. And an op-amp can be made to do all sorts of different things just by hanging resistors and capacitors and diodes and God knows what else on top of it. So if you get an op-amp, it's a bit like a Swiss Army knife. It can do all sorts of different jobs. What I've got here is I've got an op-amp which is called a summer. It's a summation op-amp. I probably spelled that wrong. Anyway, what it does is it adds all the signals coming into it. So you put signals into this op-amp, and it adds them all together and outputs a value. Over on the left-hand side over here, I've got signals which can come in. These are different milliamp values. So I have all these milliamp values, milliamps. I have all these different milliamp values which can come in. Just here, I've got a digital word. Digital word. I've got a digital value. What I'm going to do is I'm going to use my DAC, my digital to analog converter, to change this digital word into a 4 to 20 milliamp value. Each one of the bits on this digital word is connected to a switch, so that if the bit is off, the switch is open. But if the bit should come on, the switch will close. Okay, at the moment all of these switches are open. The only value I've got coming in is this 4 milliamps, so the only value going out is this 4 milliamps. Okay, what I'm going to do is I'm going to stick a different digital word in. Dump. Now, I've got a different digital word. Everywhere where there's a 1 on my digital word, the corresponding switch is closed. So I've got a 1 there and the switch is closed. I've got a 1 there and the switch is closed. I've got a 1 there and the switch is closed. And a 1 and the switch is closed. And whenever I've got a 1, the milliamp value passes through. So now, what I'm going to do, what my summation op-amp does, is it adds all of the signals coming in. So what I've got is, I've got 8 on that one, 4 on that one, 2 on that one, 0.25 on that one, and 0.125 on that one. And my summation block adds all of those together, and also the 4 milliamps that's coming in always on the top, and it gives me a milliamp output of 18.375. So that's how a DAC works. It's simply a bunch of switches and a special type of op-amp which allows you to do addition. How are we doing with that? Is everybody happy so far? Sorry, can you hear me now? Okay, that's better. Sorry about that. Let's start that again. Okay, what we have here is another type of op-amp. This type of op-amp is called a comparator. A comparator, what it does is it looks at the two different signals coming in. So I've got one signal here and one signal there. And when a comparator sees both of these signals are the same, it puts up a little flag, which is a little stop flag. So this is another type of op-amp, yet another type of op-amp. There's lots of different op-amps, and electronics people will explain it to you. So what we do here with an ADC is the first thing we do is we get a DAC. This part of it here, that's actually a DAC, a digital to analog converter. And what we do is, just here, this is the signal. This is the signal from the field. So this thing here, this is the signal from the field on the terminal block. And this is a digital to analog converter. So what we do is, the signal from the field comes in. We put 0 in the counter of the digital to analog converter. And of course the signal coming out is 4 milliamps. We then increment the counter. So the counter starts counting up. And as the counter counts up, the milliamp value coming out of here increases and increases and increases. As soon as the milliamp value coming out of here is the same as the signal coming from the field, the op-amp says stop. And it stops the counter. Now, once it's stopped the counter, whatever happens to be in the counter must be the digital equivalent of whatever happens to have come in on the signal, because they both generated the same number of milliamps. Now, to explain that a bit more, I'm going to do an example. supposing we've got 12 milliamps coming in here. So just here, signal from the field is 12 milliamps. What we do is we start the counter, and the counter starts, and the signal coming from there starts at 4 milliamps, and as the counter increments, that signal goes up and up and up and up and up. And then eventually, that signal will get to 12 milliamps. Now, when we've got 12 milliamps here, and 12 milliamps on the bottom, the op-amp says stop. And as soon as the counter stops, whatever happens to be in the counter is taken as the signal through. And the counter, if it's an 8-bit counter, would contain, in this case, somewhere along the lines of 1, 2, 3, 4, 5, 6, 7, 8, something like that. And that digital value will be sent off to the PLC. So an ADC contains a DAC, and the DAC increments until the signals are the same. There's a few other options rather than having a counter which starts at the bottom and increments. Sometimes what you do is you have something which doubles each time and then backs off. There are other sort of strategies. But basically we have a digital counter that counts up, and as soon as that counter's got the same value in it that generates the same number of milliamps as the signal coming in, then we say stop and we send that through to the PLC. Now, important question. Is an analog signal continuously monitored, or is it just occasionally sampled? Okay, because each time we have to restart the counter, wait for the counter to get to the value, and then pass the value through, then restart the counter, wait for the counter to get to the value, and pass the value through, ADCs sample. Now that might not seem too significant, but in actual fact it changes absolutely everything. And when we get to doing PID, which I think we're going to be doing next week, you'll see that sampled signals means all bets are off. Now, it's actually even worse. The ADC is only sampling the signal. But PLC manufacturers are cheapskates. If you have a PLC with 8 analog inputs, you won't have 8 ADCs. What you'll have instead is 1 ADC and a multiplexer. A multiplexer is like a telephone exchange. It just says, okay, ADC 1, ADC 2, ADC 3, 4, 5, 6, 7, ADC 8, and then goes back to ADC 1. It's a telephone exchange. It just picks one of these inputs at a time. And each one of these inputs is connected to the actual ADC. So that if the ADC itself takes 20 milliseconds to sample, but you have 8 of them, then in fact you only get to each ADC every 8 times 20 goes. 2 8. So you only get to each ADC every 160 milliseconds. So you have to be aware of that. ADCs, you may see a manufacturer say, oh yeah, we're sampling the ADC every 200 milliseconds or every 20 milliseconds, but they're actually not. Because if they're multiplexing, they're only sampling one of them at a time. Each individual ADC is 20 milliseconds, but the entire ADC input board will be, each input will be only sampled every 160 milliseconds. Of course, you can always buy faster ADCs. You can always buy faster ADCs. You can always buy better ADCs. But there's a price to be paid. So you've always, what I'm trying to tell you here is you've got to watch PLC manufacturers